Okay, 6.4, exponential growth and decay. So this is more diffuse. And this time it's gonna deal more with the exponential function e. Okay, so differential equation is of the form dy dx equals f of y times g of x. So basically, it looks like a function with y in it and a function with x in it. We always separate the variables by writing it in the form, and then you can see 1 over f of y dy equals g of x dx. The solution is found by anti-differentiating each side with respect to its thusly isolated variable. So here, when it said find the solution, your solution is going to basically be an equation, y equals da 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 da. Example 1, solve for y if dy dx equals x, y quantity squared and y equals 1 when x equals 1. Okay, so first off, I'm going to rewrite this like this because I like it in fraction form. And xy squared, that's actually x squared times y squared. Okay, so you can look at this as proportions if that helps you to see that basically you can cross multiply to move the dx. And that'll help sometimes when, for example, the right side of the equation is also a fraction, but for right here, it's good enough just to multiply by dx. So that goes away. So dy equals x squared y squared dx. So now what I'm doing right now is separating the differentials, the dy's and dx's and the x's and the y's. So I have all the x and dx's on the right, so I'm going to go ahead and get rid of the y squared. Okay, so now I have 1 over y squared dy equals x squared dx. Okay, so once this has been separated, I can go ahead and integrate. Okay, now 1 over y squared, that can actually also be written as y to the negative 2 power. And that's how I would prefer to write it. So then integrate. Add an exponent. Divide by the new one. Add an exponent. Divide by the new one. Plus c. So they gave me initial values in the beginning. They told me that y equaled 1 and x equaled 1. So in order to find c, I'm going to plug those in. So negative, and then y equal to the negative 1 power is basically 1 over y, right? This is this. So plug in 1. I get negative 1 over 1, which is 1, equals. And then this is also, x is also 1, so 1 cubed is 1, divided by 3 is 1/3, plus c. So minus 1/3, minus 1/3. C equals negative 1 minus 1/3, which is negative 3 over 3 minus 1/3. So negative 4 over 3. Okay, so now that I have C, that's when I'd go back to, I'm going to here, right? And I'm going to rewrite that as negative 1 over y equals 1/3 x cubed minus 4/3. And that 4/3 is me plugging in C. Okay, so now I have sort of kind of my equation, right? Because I don't have a C in it, but my equation should be y equals. So, remember I said that it might help you to see this as a proportion? I'm going to slightly write this over. This is going to stay the same, but I'm going to write the right side like this. X cubed minus 4 over 3. Because they both do have 1/3, right? So now that I see it like this, maybe it'll help you understand that in order to get y by itself, you might have to like do some algebra, like cross multiplying, because that's how you solve proportions, right? So I get y times x cubed minus 4 equals negative 3. And then to get y by itself, I would divide away the x cubed minus 4, so negative 3 over x cubed minus 4. And that's it. Here is my solution to my differential equation. Okay, example 2. Solve for y if dy dx equals e to the x minus y when y equals 2 and x equals 0. Okay, so now what's special about this one has to do with the properties of e to the x. Or sorry, not e to the x. Well, yes, but exponents. Properties of exponents. We're going to use the properties of the exponents, and what I mean is, if you have, let's see, x squared times x cubed, you should know that that is x to the 5th, right? Because all you have to do is really take these and add them. Okay, so we're going to use that property. Also, of course, so like if you had that, this is, so like you take the exponents and you subtract them. So 5 minus 3. Okay, so to start off, you separate the variables. But before separating the variables, e to the x minus y power is the same or equivalent to e to the x divided by e to the y, because according to exponential rules, you just have to, if you have the same base, you could just subtract the exponents. So that's why it was x minus y. Okay, so now if you notice, this is actually really convenient for me because I can just cross multiply to get the dy with the e to the y and get the dx with e to the x. So now I have e to the y power dy equals e to the x dx. All right, so now I'm going to integrate that I have now that I have separated the variables, the differentials. So integrating e to the y is just e to the y, and integrating e to the x is just e to the x plus c. So then they gave me some values for y and x. Oh, that looks like a u. Y is 2, so e squared equals, and then x is 0, e to the 0 power plus c. So anything to the 0 power is 1, so 1 plus c equals e squared, and I'm just going to leave everything in e. There's no need for decimals. So subtract 1, so e squared minus 1 equals c. So here's my c. So then I'd go back up here, and so the equation I found is this, but now I can replace c with what I have, or is equivalent. So e to the y equals e to the x plus e squared minus 1. So gotta get rid of the e because I need y. I need this equation to be y equals. So what gets rid of an e? Natural log. That cancels out, but then I also have to do the natural log of the other side. So now I have y equals the natural log of e to the x plus e squared minus 1. And we're going to leave that there. Solve for y of dy dx equals x over y when x equals 2, or y equals 2 and x equals 1. So same idea, dy dx equals x over y. Oh, look how convenient. The x and the y's are across from each other. So y dy equals x dx. Now that I have separated them, and this is a really important part, whenever there's FRQs with differential equations, if you do not separate the differentials, the variables, you get 0 points. Doesn't matter if the rest of the problem is correct. So now the integral to y is 1/2 y squared, right? Because you add an exponent and divide by it. And for x is going to be the same. Add an exponent, divide by it, plus c. Plug in your values for x and for y. So 1/2 y is 2 squared and then plug in for x. That's 1 squared. So 2 squared is 4. 4 times 1 half is 2. 1 half times 1 is 1 half plus c. Subtract 1 half from both sides. So I get 3 halves equals c. So here's my c. So then I would go to the equation I was found. So right here. And now I would go ahead and plug in my c. So 1 half y squared equals 1 half x squared plus 3 halves. Now, remember, you got to get y by itself. So first order of business would be to multiply both sides by 2. And by doing so, I get rid of the 1 half. So y squared, and that's why I did it, of course. And then so like 2 times the 1 half here, that's just 1, so x squared. And then 2 times 3 halves, so that's just 3. One last step. To get the y to equal, or sorry, the y squared to equal y, I'm going to have to square root. In which case, that means I'm going to have to square root the other side as well. And I end up with y equals the square root of x squared plus 3. Example 4. So this is the remaining part of the FRQ that was started during note 6.1. That's why I have this here. So the first two parts, A and B, were worth 3 points, and this part C is worth 6 points. So consider the differential equation dy dx equals x squared times y minus 1. Find the particular solution y equals f of x to the given differential equation with the initial condition f of 0 equals 3. So basically what we were just doing, so you take your, what do you call that? Your diffie-q, and I'm going to do the exact same thing. I want to get the variables on its on separate sides. Okay, so let's see. The dx is the easiest thing to do right now. So multiply both sides by dx, and this is what I get. And then get rid of the y minus 1, so by dividing. So I have 1 over y minus 1 dy equals x squared dx. Okay, now that they're separated, integrate. So 1 over y minus 1, went too far, hold on. 1 over y minus 1. See, this is in a fraction form, and the y minus 1 would have an exponent of -1, and if I were to, or sorry, it has an exponent of 1, but if I were to change that to not be in the denominator, it would be y minus 1 to the -1 power. So if I add 1 to that, it becomes 0. Okay, whenever I have that, then that's my cue to be like, oh, the integral to this is the natural log of y minus 1. Okay, then x squared becomes x cubed divided by 3 plus c. Plug in the values they gave us. They gave us f of 0 is 3, so x is 0 and y is 3. So the natural log of 3 minus 1 equals, and then plug in the 0, so 0 cubed plus divided by 3, so 0 plus c. So c is 2. So then right here, this is now the natural log of y minus 1 equals x cubed over 3 plus the natural log of 2. I'm going to leave it as natural log of 2. You wouldn't want a decimal there. At least not until the end. Okay? Just take care of it at the end. Okay, so the natural log of 2 is positive. That's why I'm not worried about the absolute value sign anymore, or symbols, or whatever you want to call them. So, gotta get the y minus 1 by itself, or the y anyway. And the way to get rid of a natural log is to use e, the exponential function. So now all of this is the exponent for e, and this is the exponent for e. Now, of course, e and natural log cancel each other out. So I have y minus 1 equals, and then I have e to the x cubed divided by 3 power. And then remember, adding exponents means that I had the same base multiplying. So for example, and I'll write it out. This right here. This is, okay, so e and then x cubed over 3 times e to the ln. Okay, so this is that. The fact that I'm adding them means that it was the same base, right? E, and then that they were being multiplied. So I want to revert this back to that. So I want to rewrite it like that. E natural log and 2. Okay? And the reason for that is because it gives me the opportunity to cancel those out. So now I have y minus 1 equals e x cubed over 3 times 2. So y minus 1 equals 2, because you should put the number 2 in the front. E x cubed over 3. Add 1 to both sides. And I get 2e x cubed over 3 plus 1. And there's my equation. And here are 6 points on one FRQ. Okay, the next part has to do with the actual exponential growth and decay part. In many applications of differential equations, the rate of change of a variable y is proportional to the value of y. If y is a function of time, the proportion can be written as dy dt equals k times y. Okay, so you will see many problems with this. And you need to be able to actually go ahead and identify that as being the rate of change of y, because dy dt is a derivative, and that is the rate of change. Rate of change is derivative. The rate of change of y, so the derivative of y, equaling some number times y. Okay, so now the exponential growth and decay model states that if y is a differentiable function of t such that y is greater than 0 and y prime equals ky. So basically, if this is true, which is the same as this, then y equals c times e to the kt power, where c is the initial value of y and k is the constant of proportionality. Exponential growth occurs when k is greater than 0, but it's decay when k is less than 0. You actually do learn this in algebra 1 or 2, sorry. And I'll show you why this is equal to that. So find the solutions to dy dt equals ky if k equals 1.5 and y0 equals 100. Now, y of 0, this is the initial value of y. Okay, because at time 0, at t equals 0, y equals 100. So this is the initial. Find the solution to dy dt. So dy dt equals ky. K is just a constant. It's a number. But they are telling me that k equals 1.5. So separate the variables. There's no t in here, but there's a y. So I would multiply the dt over. So dy equals ky dt. So let's move the y. So 1 over y dy equals k dt. Everything is separated because, again, so here's the dt, here's the dy with its y, right? Okay, integrate. Now the integral of 1 over y, that right there should be a cue to you that, oh, it's the natural log. And then if I integrate k, if k is a constant and I'm integrating it, then by integrating it, I'm going to go ahead and actually introduce t to this function, right? If this was the number 4 and you integrate 4, it's 4x, right? So it's k and integrate it, and I'm working with t, so kt plus c. So then this is where we would go ahead and plug in the 0 or sorry, not the 0. I would plug in k equals 1.5 and I would use my initial value there. But the thing is, I don't want you to do this in differential every single time. That's not the point. There's a reason for what was on the previous slide. So we're not actually going to find C. We're going to leave C there, and I want to rearrange this so that you could see why it is that I don't want you to do this integral. I expect you not to do this integral. The only reason you should do this integral is if they ask you to prove that dy dt equals ky is equal to y equals this part right here, y equals c times e to the kt power. Okay, so we're not actually going to find c. So I need to let this look like y equals something. So natural log, I need to get rid of it. And how do you get rid of it? By introducing e. So this will cancel out. And now I have to introduce it to the other side also. Okay, so now I have y equals e. Now remember, I said it before. This and this are being added. They're both the exponent for e. So originally it would have been, okay, so e to the kt power times e to the c power. Now what is c? C is a constant. C is a number. It's just a number. I don't know what number it is. It doesn't really matter. Not right now. Now, e is also a number. E to the c power, so this right here, this in reality is just a big old number. So it doesn't really matter what number, it's a number, it's a constant. So instead of using e to the c power, what we're going to use is we're just going to use one big fat c. So y equals e to the kt power times c. And so then y equals c times e to the kt power. I don't expect you to do this differential every single time. I expect you to see, OMG, dy dt equals ky, so straight from there, I need you and I expect you to go ahead and be like, okay, so y equals c times e to the kt power. Okay? So now that I'm going straight there, that's when I start using the values that were given to me. K equals 1.5 and y of 0 equals 100. Remember, the big C is the initial value of y. So y equals 100 e to 1.5 and then t. And this is the solution to dy dt if k equals 1.5 and y of 0 equals 100. Remember, solution is just an equation, and in this equation I have my y and I have my t. Okay, example 6, find the solution to dy dt find the solution to dy dt equals ky if y of 0 equals 60 and y of 10 equals 30. Okay, so y of 0, this is my initial value. Initial value of y. Okay. Once again, we have dy dt equals ky. So that is right there, your cue to be like, okay, y equals c times e to the kt power. My initial value for y is 60, so I have 60 e to the kt power. Now this is my equation, kind of, but if you notice, well, I'm missing something, right? I'm missing k. I don't have my k. So in order to find my k, which is what I need to actually complete this equation, I'm going to use the values that were given to me, this right here. And they translate like this. T is 10 and y is 30. So I'm going to go ahead and plug those in. So 30 equals 60 e, and then t is 10, so 10k. So here I have every number except for k. So my job is to get k by itself, so then I can go ahead and write out the rest of my equation. So I repeat, here's my equation. This is my equation. This is my solution. problem is I'm missing this little dude right here, k. So I'm going to use the blue expression down here to figure out what k is. And I'm going to do that algebraically. So divide by 60, divide by 60. 30 divided by 60 is 1/2. 1/2 equals e to the 10 times k power. Want to get rid of e, right? Way to get rid of e is natural log. So natural log and natural log. These go away. So now I have the natural log of 1/2. So natural log of 1/2 equals 10 times k. Want to get k by itself? Got to get rid of the 10. Get rid of the 10 by dividing by 10. So I have the natural log, oops, that doesn't look like L. I have the natural log of 1/2 divided by 10. And that's what k equals. And then at this point, you would actually have to plug that into the calculator. And you would get some yucky little decimal. Okay? All right, so I plugged into the calculator and I got negative 0.06931. Now, k is negative. So what's happening here? And this is a exponential decay. But anyway, this is what I was looking for, and that's the only thing I need to complete my equation. So I'd go back, so negative 0.06931, and remember this right here was supposed to be my equation, but I was missing k. So to complete it, you're actually allowed to say, oh, here's my equation, and k equals negative 0.0, I already forgot what it was, 0.693. 1. You can actually say that. You can like, okay, y equals 60 EKT, or power, k equals whatever. Okay, you can do that. Or you can not be lazy, I guess, and then write it out. T. And I know that in this class you're supposed to round to 4 decimal places, but sometimes k might have 4 zeros after the decimal. So just put enough of the number there to be safe. Okay, next. Example 7, the rate of change of y is proportional to y. Okay, those words, this right here, the rate of change means dy dt of y is proportional, is equals proportional, so it's a proportion, so it's some kind of multiple to y. Proportional, right there, and then y, right there. Okay? So basically, we're going to be working with y equals c times e to the kt power. They're telling me some stuff. They're telling me when t is 0, y is 2. So that's the initial value. I'm going to move this over. So this is the initial value of y. So basically c. And then they're also telling me that when t is 2, y is 4. What is the value of y when t equals 3? Okay, so for my equation, I've got y equals, my initial value is 2, e, OMG I don't have k, and OMG I don't have t. So then I would actually be finding k. And then that's why they gave me these values. I'm going to use those to find k, just like I used them in the previous example. So let me move this over here, and then, okay, so that's what I'm going to use. Okay, so y is 4, 2, e, I don't know k, but t is 2. I'll just write the 2 in the front. Okay, so solve for k. So divide by 2, right, to get rid of the 2. So I get 2 equals e 2k. To get rid of the e, I'm going to have to do natural log. So natural log of 2 equals 2 times k. Divide by 2. So the natural log of 2 divided by 2 equals k. Again, decimal time, right? So calculator time. And yeah, you'll need a calculator for this. Use the calculator, and by the way, this is an exponential growth, right? Because k is bigger than 0. So there's my k, so now I can go ahead and complete my equation. um, up here somewhere. Okay, so my equation is y equals 2e, and then k is 0.3467 t. Now, I'm not done because in this problem, I actually wasn't asked to find the solution, or y equals. What I was asked to do is, what is the value of y when t equals 3? So what is y equal when t is 3? Not difficult at all. Y equals 2 times e to the negative 3, 4, 6, 5, 7, right? 0.34567 times t, which is 3. And then solve that. And of course, calculator. And that'll be, and there you go, rounded to 3 decimal places. Okay, last example. Suppose that 10 grams of the plutonium isotope 239Pu was released in the Chernobyl nuclear accident. How long will it take for the 10 grams to decay to 1 gram? And then they give you a piece of information that you kind of need. The half-life of 239Pu is 24,100 years. Okay, so this, believe it or not, is just like the previous couple of examples. So there's 10 grams of this plutonium, and we want to figure out how long will it take for the 10 grams to decay down to 1 gram. Okay, so you're going to use the growth and decay model, which is this. And the thing is that in this problem, I'm trying to figure out when will this equation equal 1? Okay? When will y equal 1? So we're going to have to find some stuff. And they did tell me the half-life of this plutonium isotope, how long it takes to get to the half-life. So the half-life is how long it takes for the original amount to decay down to half of it, right? To half of the original amount. So half of the original amount is 5 grams. So this equation will equal 5 grams when, right? Or after, I should say after 24,100 years. Now the question is, what is C? Here's E, and then what is K? Now C, remember C means the initial value of Y. Well, Y in this case is the grams of the isotope, and initially there were 10 grams. K, however, we don't know. And that's what we're going to have to find, just like the previous two examples. So divide both sides by 10. So I get 1/2 equals E, and then it's customary always to put numbers in the front, right, of the variables. Got to get K by itself, so got to get rid of the E. And the way to do that is natural log. So natural log of here, natural log of that, put by to the E. So natural log of 1/2 equals 24,100K. Get rid of the 24,100 by dividing both sides by that. And K would equal the natural log of 1/2 divided by 24,100. And that's calculator time. So I put that in the calculator and look at this lovely number of decay that I got. Negative 0.0000287761. Those are all the numbers I got on the calculator, so I'm using all of them. So there's my K. So now, remember, the whole point of this problem was to figure out when this equation would equal 1. That's why I have that lonely 1 over there. But I needed an equation to begin with. So now I have my K, I have an equation. Y is going to equal 10, because C is 10, times E. K is, so negative 0.0000287. Okay, so 28761 times T. And in order to figure out when this equation is going to equal 1, at this point, all I need is T. The T, right? The when. So this equation is going to equal 1. So 10 E this horrible little k value. So my job is to figure out what t is. So divide by both sides by 10. So I get zero point 0.1 equals e to negative 0.0002871 power times t. Got to get rid of the ln, the e, and I'm going to do that by introducing ln. So now negative 28761 times t equals the natural log of 0.1 or 0.10. Divide the k from both sides, right? That horrible little k. I'm not going to write it again, sorry. And t will equal whatever the natural log of 0.1 divided by negative 0.000028761 is. And calculator time. So there's what I got on the calculator. 80,059.2849. In case they ask for an approximate time, this is roughly 80,059, and this was in years. And that's how long it would take for the plutonium to decay from 10 grams to 1 gram. Okay, homework. I want you to answer the following FRQ to the best of your ability. And that is your homework. And I need it written out on a piece of paper. I want you to write out the entire question, every single part, and I want you to answer each section as much as possible. Show me all the work, and your answer, if possible, try to write it in a sentence, and we will go over it first thing in class. Okay? This is the first FRQ that you're actually going to do by yourself, and it starts off with limits, continuity, knowing whether or not something is differentiable. Please use your notes. Any problem that you might find that is similar to it, try it. Please try it your best. Don't cheat. There's no point in cheating. There isn't. Who are you helping? Nobody, but just try to do this on your own. If you can't, then suck it up, come to class, and pay attention. Let f be the function defined by the following. Okay, it's a piecewise function. Part A, you have to determine whether or not f is continuous at x equals 3. Explain why or why not. You should be talking about limits. B, find the average value of f of x on the closed interval from 0 to 5. Average value. Okay, that's integrals. And the average value you have to do with something, it has something to do with 1 divided by b minus a. C, suppose the function g is defined by the following. So here you have another piecewise function. But there's a k in it and an m. Okay, there are variables, k and m, but these variables are basically just numbers. Your job is to figure out what those numbers could possibly be. And then they tell you if g is differentiable at x equals 3, what are the values of k and m? In order for a function to be differentiable, the left side or both of these derivatives have to be equal. The left-hand derivative has to equal the right-hand derivative. But also remember, in order for a function to even have a derivative, it has to be continuous, which means the left limit has to equal the right limit. So you're doing that. Two different things. It's a system of equations, basically. You're trying to solve by using continuity and differentiability. Not impossible. Can be done. This question would be worth 9 points on the AP exam. Okay. I do expect this at the beginning of class. Before I go over it, I will be looking at all 10 of your papers to see what you did. Have a wonderful evening.